Module 2, Control Systems and their applications in manufacturing. 2.1 Introduction to Control Systems. A control system manages, commands, directs, or regulates the behavior of other devices or systems using control loops. In manufacturing, control systems ensure precision, automation, and safety in processes such as machining, assembly, and quality control. 2.2 Input and output in control systems. Every control system has input, the desired value or command. Output, the actual response of the system. The goal is to minimize the difference between input and output, ensuring accuracy. 2.3 Open loop and closed loop control systems. Open loop systems. The output has no influence on the input. Example, an electric iron where heat is supplied for a fixed time without feedback. Closed loop systems. Also called feedback systems. The system continuously compares the actual output with the desired input and makes adjustments. Example, a thermostat-controlled heating system. Closed-loop systems are more accurate and widely used in modern manufacturing. 2.4 Examples of control systems in manufacturing. CNC, computer numerical control, machines adjusting cutting speed and feed. Automated assembly lines using robotic arms. Temperature control in furnaces. Quality inspection systems using sensors and cameras. These examples highlight the integration of control systems with manufacturing processes. 2.5 Mathematical modeling of physical systems. To analyze control systems, we model physical processes mathematically. Mechanical systems can be modeled using Newton's laws. Electrical systems use circuit laws like Ohm's and Kirchhoff's. Thermal systems are modeled using heat transfer equations. These models allow engineers to predict system behavior under different conditions. 2.6 Transfer functions and system response. A transfer function is a mathematical expression that relates the input of a system to its output in the frequency domain. It helps in understanding system stability, speed, and accuracy. System response refers to how a system reacts over time to a given input. Responses can be transient response, short-term reaction after a change. Steady-state response, long-term behavior after settling. 2.7 Stability of control systems. Stability means that a system produces bounded outputs for bounded inputs. An unstable system can oscillate uncontrollably or diverge, leading to dangerous conditions in manufacturing. Methods such as root locus, Bode plots, and Nyquist criteria are used to analyze and ensure stability. 2.8 Integration of manufacturing processes and control systems. Modern manufacturing integrates advanced processes with intelligent control systems. Examples include smart factories with sensors, automation, and feedback control. Adaptive control in machining, adjusting speed and feed in real time. Robotics in assembly lines, guided by control systems for precision. This integration is at the heart of Industry 4.0, where cyber-physical systems and the Internet of Things revolutionize manufacturing. Conclusion. In this course, Manufacturing Process and Control System, we explored both the physical methods of making products and the control systems that regulate these processes. In Module 1, we discuss forming, shaping, machining, casting, powder metallurgy, surface treatment, non-conventional machining, and jigs and fixtures. In Module 2, we introduce control systems, distinguishing between open-loop and closed-loop types, studied inputs, outputs, transfer functions, system responses, and the importance of stability. We also saw how control systems are applied in modern manufacturing. The key lesson is that manufacturing and control systems are inseparable. Efficient production requires not only the right processes and equipment but also intelligent systems to regulate and optimize them. Together, they form the foundation of industrial engineering and modern technological advancement.